In this illustration, we'll analyze the heat and work done in a linear process by the gas. Here, figure shows the indicator diagram of a thermodynamic process on n moles of a monoatomic gas along the linear path AB. An initial pressure is given to us, final pressure is not given, and the volumes in states A and B are given. We are required to find the amount of heat supplied to the gas and work done by the gas in this process. Here we can start with the relation in P and V. Here from the given indicator diagram we can see pressure is given as kV, as there is a linear relationship, and here this implies PV2 power minus 1 is a constant. So here we can write the polytropic constant is minus 1, as it is PV2 power n is equals to constant form. So this is a polytropic process in which molar specific heat of gas will be a constant. So here we can write the polytropic constant. We can take it as m, and that is equals to minus 1. So using this we can find out the molar specific heat of gas is this. We already studied in concept videos, which is Cv plus R by 1 minus m. So here for a monoatomic ideal gas, Cv is 3R by 2 plus if we put m as minus 1, this will be R by 2, that is equals to 2R. So if we are having the value of molar specific heat, we'll find out the heat supplied if we know the initial and final temperatures. So first we calculate the pressure as in given process P by V is a constant. This implies here we can write P0 by V1 is equals to P final by V2. As initial volume at V1 pressure is P0, and for volume V2 if it is P final, this gives us the final pressure in a state B, which is P0 V2 by V1. If we have got the final pressure in a state B, then we can easily find out the temperatures also. By gas law, temperatures in states A and B are, here I can write temperature in a state A is P0 V1 by NR, and temperature in a state B is pressure in a state B, which is P final V2 by NR. If we substitute the value of P final over here, this gives us P0 V2 square by NR V1. So as we have got the temperatures, we can directly calculate the heat supplied to gas as Q is equals to NC delta T, and that should be NC TB minus TA. If we substitute the values, this heat supplied, we can get this value of C we can put as NR. So this 2 NR multiplied by this TB minus TA, if we substitute it as P0 V2 square by NR V1 minus P0 V1 by NR. Here you can see this NR gets cancelled out, and simplifying this will give us 2 P0 multiplied by V2 square minus V1 square by V1. This is one result of the problem, the amount of heat supplied. And here if we carry on and calculate the work done by gas in the process, and work done we can write the amount of heat supplied minus the increase in internal energy. So on substituting the value of Q and delta U, work done as N, the C minus CV multiplied by delta T. As C is 2R and the value of CV is 3R by 2 for a monoatomic gas, here we can write work done as N multiplied by R by 2, and delta T is the same term we are writing over here, which is P naught V2 square by NR V1 minus P naught V1 by NR. Here also this NR gets cancelled out. And on simplifying, the value of work done we are getting is P naught by 2 multiplied by V2 square minus V1 square by V1. This is the final result of this problem.